So Frank Wilczek is spending time in Stockholm, and he has very kindly agreed to give a talk here at our meeting. I hope this short introduction is good enough for you, Frank.
What's that?
Is that short introduction good enough for you?
I'll take what I can get.
It'll be a completely different topic, but we look forward to hearing it.
Okay, thank you very much. So, thank you for inviting me. This talk will be about amplitudes, a rather broad subject, if I may say so. And what I'll be talking about is anyons in action, and how they control threshold behavior, how they will control the behavior of measurable quantities of great interest in condensed matter physics. This is work done with Ari Turner, Frank Polman, and Siddharth Morampudi, the last two of which I've never met. I look forward to this. So I'll be making a number of very unusual assumptions. N equals 0 supersymmetry. U1 gauge symmetry. 1 is much, much less than infinity. And the U1 is going to be electromagnetism. 2 plus 1 dimensions. And I really mean 2 plus 1, not Lorentz invariant. Not even translation, lattice systems, solids. It will be a large N, which is the number of underlying particles, electrons. We will get to a kind of continuum limit and unusual phases of matter. And we'll be discussing emergent particle degrees of freedom. We won't be dealing with a very large number of underlying particles, electrons, let alone quarks and gluons, but just interesting emergent particles. So I'm going to start from scratch. This will be a kindergarten lecture compared to the ones I've heard. So there'll be no conformal symmetry in 17 dimensions or whatever. And I'll try to make it all self-contained. So, in 2 plus 1 dimensions, quantum kinematics allows new possibilities for quantum statistics besides bosons and fermions. There are many ways of looking at this. It's a very special property of 2 plus 1 dimensions, of flat land. First, thinking about the world lines of particles, the relevant classification of their topology in 2 plus 1 dimensions is the braid group, and that goes beyond the group of permutations which you have classifying the topology in 3 or more dimensions. I should say in 1 plus 1 dimensions, the idea of quantum statistics is a little ill-defined because you can't have particles slowly move past each other or around each other without them intersecting, so statistics can't be separated from local interactions. Another thing that's special about 2 dimensions is that the rotation group is abelian, and so you can have offsets in the quantization condition. There's no nonlinear commutator to cramp your style. And probably the most fruitful way of thinking about it is that in 2 plus 1 dimensions, flux tubes become point-like so that one can have Aharonov-Bohm type effects for particles. Particles can have magnetic flux, and particles that carry both charge and flux will have funny phases as we move around one another. This can be realized either for abelian or non-abelian fluxes. And interestingly and crucially for what will follow, you can also have mutual statistics for non-identical particles. You can have funny phases arising for what happens when a particle of one type circles around a particle of a quite different type. So that's a quantum statistics that doesn't require indistinguishable particles. Here's a picture of electrons reacting to this change in their very basic identity. But we're merciless. So let me first discuss the quantum Hall effect complex briefly to tell you, to first reassure you that these ideas have an instantiation, but then secondly to say why we'd like to do better. So in the quantum Hall effect, we have anyons, but not much action. So I won't review this subject, but there's a vast literature going back 30-odd years now that quasiparticles in many fractional quantum Hall effect states are firmly predicted to embody these new possibilities, fractional and even non-abelian statistics. Sadly, however, the experimental consequences have been kind of meager. Back in the 80s, when I was first thinking about these things, I thought within 6 months we'd have these experiments. This is not the LHC we're talking about, but tabletop materials. But really, it has not turned out that way. The experiments are very difficult. People are still trying, but and very hard, and they will succeed. But it's been an uphill slog. And there's a simple and profound reason behind this, is that in the fractional quantum Hall effect realization, the anyons are basically fractions of electrons that carry the fractions of electron charges, and electric charge is a daunting complication. When you have particles that are electrically charged, even if their charge is, say, E/3, a third of an electron, they still get pinned to impurities. They get pinned to positively charged impurities, so that makes it hard for them to move. And if they can't move, you're not very sensitive to their statistics. They're highly unfree, even if they're not pinned to impurities, because the quantum Hall effect takes place in a large background magnetic field, and charged particles don't like to cross field lines. And also, last but not least, if you can get around those things, the effect is subdominant. The effect of quantum statistics, if you think about it, you're changing a phase by a finite amount as you go around 2 pi, or you can think about the effect on angular momentum. So there's a kind of centrifugal barrier modification. Those are 1/r² effects at long distances. They're subdominant to the just plain charged particle 1/r Coulomb potentials. There may be ways to work around those difficulties. In appropriate quantum fractional, these things are under investigation. In appropriate fractional quantum Hall effect states, you could change the quasi-particle statistics without changing their charge. If you can do that, that removes many of the complications. Or you can wait for the spin fractional quantum Hall effect, where the quantum quasi-particles are often electrically neutral anyons, and that will happen too. Or you can just show true grit, as some of the experimentalists are doing, and just try to overcome these difficulties by hard work and quantitative analysis. But here I want to discuss another radically different possibility. And this is a different class of materials that are 2 + 1 dimensional, called spin liquids. So it's widely expected on the basis of numerical work and theoretical analysis, that several two-dimensional materials should exhibit spin-liquid phases. Now, what a spin-liquid is exactly is not clear any more than it is clear exactly what a liquid is, think about it. But we know what a solid is, and the spin analog of a solid would be something like an antiferromagnet or a ferromagnet that has lattice order and rigidity and an order parameter. A lattice gas is what happens if you heat up a lattice solid, and it just becomes totally disordered. And in between, there might be a spin liquid. But of course, that's extremely vague. In the examples of interest, and I'll show you a very concrete model momentarily, the qualitative features that these spin liquids have in common are the formation of a gap to excitations. So the magnons go away, and the spins are not free either, so you have a gap for excitations. A high degree of quantum entanglement, which is responsible for this exotic behavior, and the absence of a local order parameter. I put an asterisk next to the gap because some people also refer to states without a gap as spin liquids, but I think that's really confusing. For this lecture, in any case, I'm going to assume we're talking about the kinds of spin liquids with gaps. Now, several of these candidate spin liquids include quasiparticles with unusual quantum statistics, the kind of thing I mentioned in the beginning. And that provides, in principle, precise characterizations as signatures for those universality classes. For these kind of vaguely defined ideas, we can have precise consequences about the quasiparticles. Now, I thought it would be a good idea to show you a simple, exactly soluble model that leads to a phase of this kind, so it's not all vague hand-waving. This is something called the toric code model, and I can develop it from scratch before your eyes. The version I will show you is solvable, it's unrealistic, it contains many body interactions, as you'll see, but it's believed that, well, it's very strongly believed, and in fact proved, that you can perturb around this model, keep its qualitative features, and that it's a big universality class that can be realized with realistic interactions, and in fact is plausibly realized already in an existing material. In this universality class, there are two kinds of quasiparticles. For reasons that will become obvious, they're called magnetic and electric. Both are electrically neutral. We're talking, I didn't say it explicitly, it's been implicit, I hope, that we're talking about spin systems, so looking systems with localized spin. So they're electrically neutral excitations. Separately, they're bosons, so not interesting just from the point of view of quantum statistics, but there's a non-trivial mutual statistics. When M goes around E, and one of the magnetic particles goes around one of the electric particles, there's a minus sign. This is not, by the way, fermions. Fermions is not when one goes around another, you get a minus sign. It's when one is exchanged. This is like half a fermion, so often called a semyon. But the particles are not identical. Anyway, as a consequence, as you can easily work out in your head, the relative orbital angular momentum for these guys is half an odd integer. That's the key consequence of having this mutual statistics. Okay, so now I'm going to switch over to slides from a presentation I gave to my class years ago about the toric code model. The hardest part of understanding the toric code model is just keeping the different operators in mind. So I've given you a handy crib sheet over here. There'll be 4 kinds of operators that appear in the discussion. We're talking about a system, a lattice, where the spins live on links. It's just a square lattice in 2 dimensions with spin 1/2 objects on the links. And we want to define 2 kinds of operators that will appear in the Hamiltonian. The A operators are associated with points on the lattice, and what they do is multiply the variables on the links that are emerging from that point, the so-called star of the lattice point, by sigma x. The B operators are associated with plaquettes on the lattice, or, if you like, with points on the dual lattice. And what they do is multiply the links on that plaquette, or surrounding that dual point, by sigma z's. They all commute, and their eigenvalues are plus or minus 1. Now, there's some reference in these slides to protected states. That's because of interest in this model for quantum computing and memories, which I'm not going to go into. For us, a protected state in this context just means a ground state. So the ground state of that Hamiltonian, which is simply minus all the A sub s's associated with all the sites, minus the B's associated with all the plaquettes, the ground state of that Hamiltonian, which is, by the way, manifestly gapped, because the eigenvalues are discretely separated. Well, it's gapped in any reasonable sense. I should say that the ground state is 4-fold degenerate. Okay, so the B equals 1 equations, you can easily convince yourself that I have a very simple interpretation in the basis where we take the spins to be in the z direction. We look at the eigenstation in the z direction. It just says that the number of down or up spins on the links of any plaquette must be even. That leaves a massively, if we just had the minus B Hamiltonian, we'd have a massively degenerate ground state at that point. But we have to apply also the A equals 1 equations. That will set the coefficients of many of those configurations equal. One can analyze exactly what their effect is by a procedure very similar to gauge fixing. So if you take a maximal tree on the lattice and apply A operators to a state on which all the B's are equal to 1, you can set all the spins on the links of a maximal tree equal to 0. I'll show you this in pictures momentarily, and that'll make these words clearer. So here's a concrete maximal tree. And if we follow the recommended procedure here, of running along the top row, which is also identified with the bottom row, setting the spins, using the A operators to set spins equal to 1, because we're looking at things which are eigenstates with all the A's having eigenvalue 1, we can use the A's to simplify the coefficients, project them on a reference state. So we can go along the bottom row first, systematically setting those spins equal to +1 up direction, and then go along the columns. And you can convince yourself that doing that you never undo anything you did before. So you can set all those spins equal to 1. And then once you've done that and look back at the b equals 1 condition, you find, so on the maximal tree, we've set all the spins equal to up, but we still have the condition that the number of up spins or down spins on any plaquette is even. So if we have spins up or down, I forget which one I picked, on the red links, then if you look here, you see we have 3 that are up. So if an even number is going to be up, this one also has to be, I'm sorry. Sorry, I'm having a mind blank. The upshot of the analysis, if it's done correctly, is you find that there are, the constraints give you the condition that the spins on the blue links are all up, and the spins on the green links are all equal, but they could be either up or down. And then similarly, these yellow links can be either up or down, but they all have to be equal. So there are 4 ground states. This is not the central point of interest for us, true fact. The central point of interest for us focuses on not the ground state, but the excitations. And we're going to consider 2 kinds of operators that will produce excitations. These are string-based operators. That is, they're defined on paths. Okay? And the X-type operators are strings in the dual lattice. So you take a path in the dual lattice and take all the links that that path intersects and multiply those by sigma x's. That's what the X operators are. And the Z operators are simpler to define. You take a string in the actual lattice and just multiply by a product of sigma z over all the links on that string. So the B operator will look like this. This is a closed loop of B operator. It doesn't have to be closed. And this would be an A operator. And you see, you're multiplying by sigma x's. I'm sorry, an X operator. You're multiplying by sigma x's on these dual links. For those of you who studied homology, which in this crowd is probably everybody, this is a poor man's version of homology theory with the Poincare dual already present. So now we get to the excitations, which is the interesting bit for us. So since the A's and B's commute with the Hamiltonian and with each other, we can diagonalize the Hamiltonian using their eigenstates. We've already projected or analyzed that the ground state is 4-fold degenerate. And then the excitations will be things that have a minimal number of those spins disturbed, okay? Disturbing a minimal number of either A or B operators. Due to global constraints on the A's and B's, it's impossible to frustrate just one. You can easily convince yourself of that. The minimum is 2, and in fact, the way to construct the minimal excitations is very suggestive in terms of these X and Z operators, or if you like, the strings with excitations at the end. Electric pairs can be created by open Z-type operators. So if we have, that's a string in the actual lattice, multiplied by sigma z's along the string, and that will disrupt the A operators, not the B. It won't disrupt the B operators because it's all multiplying by, I'm sorry, it won't disrupt the A operators because it's all multiplying by sigma x's, but it will disrupt the B operators on the plaquette that surround the end. So you'll have a -1 eigenvalue for each of the B operators at the end, and that's producing a pair of electric charges. And so the electric pairs are produced by the Z operators. I think I said that wrong. Let me say it again. As I said, the hard part is remembering which operators go with which. The electric excitations are produced by the Z operators, which we said are strings on the ordinary lattice, right? And you multiply by sigma z's along this string. And now if you apply A operators at the end, there's a sigma x, which intersects the string once, and that will have its sign changed, because it anti-commutes with the sigma z. All the other A operators, which are not at the ends, will not be disturbed because they will intersect this string either twice or not at all. So we have at the end produced a little bit of excitation, minimal excitation. They have to come in pairs, and the string can be moved around freely without any cost in energy. So it interpolates when you move the string, it's just moving you around in this highly entangled ground state, but the ends have physical significance. And similarly, you can produce magnetic excitations with open X-type operators. With X-type operators, it's clear that they commute with all the A's because they're multiplication by sigma x's, and all the sigma x's commute with each other, but they disturb the end plaquettes by 1 unit. So we can solve not only for the ground states, but also for the excited states. The general excited state is just putting down a lot of these strings. So now we can discuss the statistics of these excitations. Electric strings can be pulled through one another freely since all the sigma z's commute and all the X operators R is multiplying by strings of sigma z's. And the magnetic strings can be pulled through one another since they are all multiplication by sigma x's and those commute with each other. But the interchange of electric or magnetic particles here's a diagram in view of the time. I will not go through this detail. But if you want to exchange a magnetic and electric particle, or here in this diagram, simply to have an electric particle move around a magnetic particle, this is a bunch of sigma x's, and here at this link we have, because of the magnetic charge, the sigma z. These don't commute, and that's a minus sign. So there's a mutual statistics between the electric and magnetic particles. These emergent excitations in the simple solvable model have mutual statistics. It's a funny kind of long-range quantum gauge interaction in a gapped system. So it's the most important kind of interaction. Dominates at long distances. Everything is gapped. And that's promising for, of course, seeing it experimentally. Now, the Hamiltonian I actually showed you is not only unrealistic because it involves 4 spin interactions and no subleading terms, but also not dynamically interesting. We can analyze the spectrum, and it's in front of us, but the same thing that makes it transparent also makes it not so interesting. However, you can perturb this Hamiltonian, as I said, without disturbing the qualitative properties. You still have quasiparticles of the same kind, still have quantum, still have mutual statistics, and then the particles can move. So, again, it's a robust universality class, because, as shown in numerical experiments, similar in spirit to the way you show that QCD at strong coupling, which manifestly confines, is the same phase as QCD at in the continuum through numerical experiments. Here you can connect the toric code model, since it has a gap, in a controlled way to Hamiltonians that are more realistic and also support hopping of the excitations. In fact, there's a very well-known natural model that's actually applied to actual materials that seems to be this universality class. It's the anti-ferromagnetic Heisenberg model on a Kagame lattice. I'll show you on the next slide what a Kagame lattice is if you don't know. And there's circumstantial evidence that this phase is actually realized experimentally in the mineral Herbert-Smithite. So we don't have Calabi Yau, but we do have Herbert-Smith. This is what a Kagame lattice looks like. It's described to me as kind of being based on a Star of David overlapping structures like that. Okay, so now, how am I doing for time? Okay, good, because I wanted, this is kind of the conclusion. Now we want to get to threshold production, which is where amplitudes come in, and where I think we make an exciting connection to experimental possibilities. So the angular momentum associated with a newly opening channel, such as, specifically, the production of a pair of excitations, either electric and magnetic, or magnetic, or whatever, is directly tied up. The behavior, how fast that threshold sets in, is directly tied up with the relative angular momentum of the particles you're producing. If the particles you're producing have a non-trivial angular momentum, a non-trivial centrifugal barrier to the origin, it means the wave functions of the origin are thinned out And that means that at small momenta, where you're trying to excite these things at threshold, they're difficult to excite. And in particle physics, we know this very well from E plus, E minus annihilation, for instance. The thresholds for producing a boson have a very different form from the thresholds producing a fermion. The centrifugal barriers thin out the wave function in a computable way, basically like k to the L, where L is the relative angular momentum. Now that's, of course, a statement that's kind of abstract about quantum mechanics of continuum particles which is not what we have in the system, where we started with a lattice system and getting emergent excitations with these properties. But as in the spirit of universality and in the spirit of the long-distance behavior, being independent of lattice details, it's suggestive that you would have this property, especially since we're dealing with near-threshold behavior, so very small momenta, and we've checked it numerically in relevant cases, even though you have a lattice, even though it's not a rotationally invariant, let alone relativistic system, this threshold behavior survives. So here's what it looks like if you calculate just the idealized quantum mechanics for different kinds of excitations. The effect on the cross-section looks quite dramatic near threshold and qualitative, just the slope of these curves, or fermions, semions, hardcore bosons, which have a zero, or just bosons, which don't have a hard core, have something like this. And here is a numerical study, typical numerical study, where we turned on interactions of different kinds and saw that the threshold behavior is pretty robust, much more robust than what's going on. So, the main message here is that the angular momentum associated with the newly opening channel has a direct quantitative effect on the near threshold behavior of the production cross-section. Specifically, the cross-section sets in as k to the 2L, where k is the momentum that these guys have, the relative momentum these guys have, which goes to 0 near threshold. And it seems clear enough and clean enough that one can aspire to see these effects in neutron scattering experiments where you start to produce quasiparticles in these kinds of spin systems. It's already been seen in experiments that quasiparticles are getting produced, not the kind of magnons, single particles that you would expect in an ordered magnetic state, but so there's already circumstantial evidence for a kind of spin-liquid behavior, breakup of magnons in these systems. And numerical evidence also that they're in this universality class. But the really decisive, quantitative demonstration that you have fractional statistics is work for the future. Those are cases we know about. We know what to expect based on the event. But in other cases, there's considerable controversy about the appropriate underlying universality class. There are also cases where the quasiparticles have more exotic statistics, non-abelian statistics. All those can be diagnosed and separated out and analyzed by looking at these kinds of threshold behaviors. There are interesting complications when we produce 3 anyons, and you can access more of the dynamics in that kind of situation. So, I expect that this threshold spectroscopy of quantum statistics, the fact that you can read off unusual quantum statistics from a definite kind of experimental protocol, will evolve rapidly from a demonstration of the existence of these kinds of exotic statistics into a diagnostic tool for figuring out unusual states of matter in 2+1 dimension. So, thank you.
Thank you. Any questions? Yeah.
So is angular momentum conserved in the production of this magnetic electric pair? And if so, where is the other half unit of angular momentum?
The other half goes off into the boundary, but yes, angular momentum is conserved ultimately.
Lattice effects. So
There are also lattice effects, yeah. So I'm not sure which is dominant, but in corresponding situations in the quantum Hall effect, you excite boundary currents. So that's certainly a possibility, but also the lattice effects might absorb on the angular momentum. I'm not sure that actually works, but it might.
I have a question myself.
Yes.
So I'm wondering, in the experimental situation, is it more like a template for an experimental setup, and actually that the actual system is very different from this kind of spin model? Is that the case, or is it directly that this kind of system can actually be simulated in material?
This universality class is, I mean, not, of course, this model, but the universality class of this model is believed to be realized in definite materials, including ones that people have in their hands. The kind of evidence for that is that you've seen the production of a funny continuum where you might have expected a single particle excitation. So the magnons seem to have fractionalized. Then the numerical kind of evidence is you can take this model, take the, I'm not sure this exactly has been done, but things like this, take the Heisenberg model and tune the parameters of the interaction to get from one to the other. Now actually, that Heisenberg model, the Kagame lattice, is not, of course, on a square lattice, that you can't do, but the reasoning is that it's more complicated, which I suppressed. There's another solvable model on the Kagame lattice, which is very closely related to this, has the same qualitative behavior, and that's the one you can continuously relate to the Heisenberg model.
More questions? Is that really the case? Well, thanks a lot, Frank, for coming by.